Assalamualaikum, my name is Masras. You are watching my YouTube channel. In this series of videos, we are performing the natural gas liquefaction simulation in Aspen HYSYS. This is the last video, and in this video, we will be performing the methane liquefaction and nitrogen rejection. If I go to my case study, so that was our feed composition, and we have removed one by one all the unwanted components. First of all, we have removed the acid gases that was comprising of CO2 and H2S, and then we have dehydrated our gas by TEG, and then we have removed the higher hydrocarbons, and this simulation is comprising of the higher hydrocarbons removal. So I will use the same very simulation because it is having the same fluid package and same components. So I will be using this stream to liquefy methane, and then we will use the cryogenic distillation for the nitrogen rejection. So without a further delay, we will move to our simulation. First of all, if I go to my this case study for the nitrogen methane liquefaction, so it says that operating pressure of this system is 150 kilopascal, and we have to decrease the temperature to 175 degrees C. And the refrigeration MR refrigeration mixed refrigeration loop will be used, that will be comprising of methane and nitrogen. So again, for decreasing the pressure, I will go to this model palette, and from the model palette I will place a let down valve over here, and with this let down valve I will be defining my outlet stream pressure, that will be 150 kilopascal. So that's good. So now I can rename my this stream to depressurize methane. So here I can have depressurize methane. So that is good. So after this, to decrease the temperature of my this stream to minus 175 for the liquefaction of methane, I will use a LNG heat exchanger. So this is my LNG heat exchanger. I will double click on it. Its inlet will be depressurized methane, and its outlet will be inlet to nitrogen rejection, REG. You can write here as. After this, for pressure drop, you can write here as 0, and go to this worksheet, and here you have to specify the outlet pressure, that is will be minus 174. You can write here as minus 174. So now you can see that my this stream is converged, but my LNG heat exchanger is not converged. So before simulation of my refrigeration loop, mixed refrigeration loop, I will first perform the cryogenic distillation for the nitrogen rejection. So now after decreasing the temperature to minus 174, I will again go to this my model palette, and from separators for the cryogenic distillation I will place a you can say that reflux reboiled absorber over here. I will double click on it. Its inlet will be inlet to rejection, or its overhead will be nitrogen, pure nitrogen, NaTrOG. So that is good. And for the boiler stream, you can write that RE2. Bottom, you will be having only methane, pure methane. So that is good. So now you can see presses. Next, for pressure you can write here as 150, and for top stage pressure you can write as 140. So after this, press this next, done. So now go to this monitor tab, and here you can see that if I uncheck this box, so degree of freedom is only 1. So you have to specify only one variable for this simulation to happen, or this block to simulate. So I will specify the component column component flexion. So add spec, and here I will, and this is my stream variable, and here I don't want my methane to have nitrogen in it. So I will methane and I will specify its mole fraction to be 0.001. And after that, in I want in methane that 0.001% of what is present, nitrogen is present. So now I have specified my component. So if I press this run, so now you can see that this simulation is solved. So I will go to the worksheet, and here I will go to the composition, go to this methane, and you can see that 0.9912% of methane is present in your bottom product. So that is good separation. If I double click on it and see, so if I double click on it, go to this design, so that is good. So now if I go to this my input stream, and from the input I go to composition and see that 6935 or 6936 kmoles of present. And in your methane you are having, if I go to this basis, mole flows, so out of 69 1,636 moles, 6,771 moles of fuel. So that is good, and approximately no nitrogen is present in your this stream. So that is good separation, and that is good to go for me. So after that, the last thing in the video is to simulate the refrigeration loop for decreasing the temperature to 129 to 174 degrees C. So again, I will place a compressor over here first of all. So this is my compressor. Then I will place a cooler over here. Again I will go to this all, and from here I will place a cooler over it. Then there will be a JT valve in the pressure changers. Just place a JT valve over it. I will double click on it, and from here I will specify it as MR1 in. So MR1 in energy you can write as MR1 compressor energy. So that is good, and here you can write as MR1 out. So that is good. In the worksheet you have to specify your stream. Just give the initial pressure, initial temperature as 30 degree. Pressure you can give as 30 kilopascal, and your molar flow rate you can is initially you can give as 100 kg moles per hour. I will double click on it, and for the specifying my components. So what are the components? So it is having methane and nitrogen. So methane is 0.80, and rest is nitrogen, that is 0.20. This is again a mixed refrigerant loop. So now my this stream is converged. I have to specify the outlet pressure. So again I will go to my this case study, and the outlet pressure is 50 kg. So we have to increase the pressure to 50 kg. So here will be 50 kgs. Sorry, it is the temperature. So this is the pressure, 50 kgs. So now you can see that my this compressor is solved. So now I will use a cooler over here, and cooler, and it will be having MR1 out, and it will be JT MR1 in. So that is good. Again, energy you can write as MR1 CX. So that is good. Go to this worksheet. So it will be, again it is a cooler, so it will be using a cooling utility. So if you are having cooling water, so you can decrease its temperature up to 39 degree. So again press this 0 kilopascal, and now you can see that your this cooler is converged. So again I will give this JR in JT valve inlet, and so this is this one. and now you can write as recycle. Sorry, to LNG heat X. You can write here as. So that's good. Go to this worksheet, and here again specify the outlet pressure as 30 kilopascal. So now you can see that temperature here is 19.40. From 39 degree to it is only decreased to 19.40. So what has happened? This temperature is higher than the inversion temperature for this system of refrigerant that is having methane and nitrogen in it. So this, for the adiabatic cooling or this duty valve to perform expansion or cooling, this this temperature must be below the inversion temperature. So if this temperature is below the inversion temperature, then only be cooling will happen. If this temperature will be above the inversion temperature, then the cooling will not happen. So again, for now, for the sake of simulation, we will see that how we will be decreasing this temperature. I will see that what is the inversion temperature. So it is the minus 100 degrees C is the temperature. So here I can write here as minus 100 C. So that is good. Now if you double click on it and see that now this adiabatic cooling or GT valve has performed the adiabatic expansion or cooling. So that is good. Go to this and just rotate it. So that is good. Again you can rotate it as well. So now double click on it, and here go to this design, and here just give this as inlet. Outlet you can write here as recycle 1. So that is good. Then just give the pressure drop as 0, and that's good. Again you can see that it is having a temperature cross over here. So now again you are having a large amount of temperature over here. So again you have to increase the flow rate over here. Either you can do by adjust function. So I will try to do this by adjust function. So I will go to this. I will just close it quickly. So after this, I will go to this model palette here. This is the adjust. So I will place adjust over here. I will double click on it, and this is my. I have to change or increase the flow rate of this stream. So I will select the variable, and it is mr1 in, mr1 in. So this is mr1 in. What I want to change, I want to change the molar flow. So this is the molar flow. Adjust target variable, and this is this LNG convergence. So what is this heat exchanger? It is LNG-103. So LNG-103, again I will target the minimum approach temperature. So where is this minimum approach temperature? So this is the minimum approach temperature, so I will select it. After this target value you can give as 1, and go to this parameters. Tolerance value you can give as 0.01. Iterations you can give as 1000. Just press this start. So now you can see that my adjust has been converged, and if I double click on it, so that is the amount of molar flow rate that is required for this heat exchanger to converge. So now again, and then the one thing is remaining, two things are remaining. You can say that one thing is that we have to, if I double click on it, so we have to uh, make this cooler some realistic way, in some realistic way. So if I double click on it on this, and I can copy this, and I delete my this adjust. So that is good. So now after this I will just break my this connection, and I have wrongly broken it, so I can break it over here. So double click on it, go to this design, and here you can write this one. So now, as this is a cooler working on some utility, so now you can decrease its temperature. If you are having water, so you can only decrease its temperature to 39 degree. So now from 39 degree to the temperature that is below the inversion temperature, you will use a LNG heat exchanger. So we will use LNG heat exchanger. So now its inlet will be JRM1 and its outlet will be JT JTMR JTMR 1 in 1. So that is good. Go to this pressure drop and here specify as 0. And now go to this worksheet and specify your outlet temperature as minus 100 C. So that is good. So now you can see that your these streams are converged, but your valve is not. So double click on this, go to the design and give as this inlet. So now again you can see that this heat exchanger and this loop is converged. But now what we will do, we will use this recycle stream's temperature, that is this recycle stream is having minus 142.8 degrees C. Either we will use this recycle one stream temperature to converge our this LNG 104. So again go to this recycle and double click on it. Its inlet will be recycle 1, its outlet will be you can write here as recycle 2. So that is good. So now I will make my connections and I will double click on it and go to this rating, and here I can write here as recycle 2, and its outlet stream I can write here as MR1 compressor recycle. So that is good. Again I will specify pressure drop as 0. So now again you have to increase, if I make it fit to screen. So now you have to again for the convergence of this LNG ETC, you have to increase this flow rate. So you can again use a adjust function over here, but I can just give a hit and trial value for the simulation. So it is, if I double click on it and see that, go to the worksheet. So it is 60. I place a value over here as 15,000. So now you can see that I have placed a random value, and now you can see that this is also converged. So now you can use the adjust function over here, but I haven't used for this. And now one thing is remaining is to give this stream recycle back to your this compressor. So again place a recycle over here and double click on it and MR1 recycle, and what will be your, this is MR1. So now you can see that this simulation is converged, but this stream is having a problem. So if I let me break it for now. So double click on it, go to my this design, and here I will make my connection is recycle. So now you can see that sometimes it happens in HYSYS. So now you can see that my this refrigeration loop in which we have reduced the temperature of methane is also converged. And the speciality of this loop is that we have used this stream temperature to converge or to decrease the inlet as the upstream of jetty valves inlet streams temperature. So this is our methane, and this methane is present at minus 156 degrees C at in the that you can see that no vapor phase is present, it is present in liquid form. If you decrease the pressure, if I decrease its pressure to 100 kilopascal or atmospheric, so its temperature will decrease to a more lower value or approximately equal to 160 or 162. So if I go over here, place a block over here and double click on it, its inlet will be a methane, and here you can write as pure methane pure, and you can write here as go to this worksheet and give its pressure as decreased pressure as 100. So now you can see that its temperature is decreased to minus 161.8, that is the temperature at which liquefied natural gas is stored or transferred. So that's all for this series of videos in which we have performed the natural gas liquefaction or methane liquefaction. I hope you liked the series of videos. Please like and subscribe my channel. Inshallah, meet you in another series of videos. Assalamu alaikum.